Let's welcome Matt, who will tell us about ITK-Wasm for Universal Spatial Analysis and Visualization. Matt, take it away.
Thank you so much. I'm very happy to be here with you, and I hope you enjoyed the conference. I have too. And I'm excited to share with you in this last session here how this project, ITK-Wasm, is intended to make WebAssembly for scientific computing accessible, sustainable, and reproducible. First, who am I and where am I coming from? I'm a maintainer of a project called the Insight Toolkit, ITK. It's a 25-year running community effort to bring the power of open science and n-dimensional spatial analysis to the world. And I'm also just a passionate serial open source contributor to many projects in our community and ecosystem, like Scikit Build Core, which was a talk earlier today on build systems for scientific computing in Python, CMake, which is a build system that was created for ITK open source, is now used throughout the world for C++ and C projects. And I've been a very active and proud SciPy community member since around 2010. And I'm old, is kind of the summary there. And throughout all this time of working professionally and passionately as a research software engineer, a few prominent lessons learned stand out in my experiences. The first is that this vibrant and dynamic synergy of the SciPy and broader open science communities, along with the open source software ecosystem, has enabled amazing advancements such as artificial intelligence and a general understanding of our world. Very proud. I think we should be very proud of that. At the same time, even with all these incredible advancements and the progress that we've made over the years in areas with developments like CondaForge and Scikit Build Core, building and packaging the associated maintenance requirements for scientific software is burdensome. And for scientific packages, for example, this means we have to build and deploy ARM and AMD64, and with additional instruction sets out there, multiple versions of Python. If you're looking at Python, Mac OS, Windows, Linux, mobile operating systems, then continuously update these packages as the platforms update. And it is painful and just a tremendous amount of work. So this inherently limits the sustainable adoption of advanced computational techniques that can improve the world. And despite this, as we've seen with this AI revolution that people have realized in the last year that many of us have known about for a long, long time, there are many non-computer scientists, even in spite of having things like accessible languages like Python or peer teaching initiatives like software carpentry, educational resources like MOOCs, there's still a vast number of non-technical researchers and members of the general public who find the capabilities of scientific open source software out of reach. And non-technical people have a hard time grasping the full power, often due to installation and coding hurdles. So how do we address this situation? We all appreciate, I think, the openness and accessibility of knowledge and innovation fostered by web technologies. So it's evident that the universal access and interoperability provided by open web technologies has the potential to transform the sustainability and accessibility challenges of scientific software. Here we have an example in this interactive open science figure available on a website. This was made with ITK.js, the predecessor to this ITK-Wasm project. And in this case, the sustainability and accessibility of this interactive open science figure is remarkable, I think, thanks to open web technologies. There's no installation, zero installation, like a web application. Any reader can reproduce these figures, and even more so, as discussed during the keynote, reuse the methods on their own data to understand how they work and gain their benefits. This is a advanced denoising, image denoising method, noise reduction method. And it's continued to function when it was created 9 years ago without any maintenance. And I think this demonstrates the potential of open web technologies to improve sustainability and their resilience. So what I'd like to talk with you today is WebAssembly, a technology that's come to the forefront in recent years. WebAssembly, usually called WASM or WASM, tomato, and it's widely supported now across all different computing systems. And it's a technology that offers high performance and a compact binary size to support multiple languages, hardware independence, security, universal platform support, and it enables developers to bring near-native speeds and portability to applications for the web, but beyond. And what is ITK-Wasm? ITK-Wasm brings these WebAssembly capabilities to scientific computing. So first we'll give you a background, a primer on what actually is WASM. Then we'll discuss how WASM addresses these challenges that are special to scientific computing. And then we'll look at the capabilities that this can bring with an example from large-scale microscopy, and conclude with a little hint on what is the future of WASM. That is what I think is really the future of scientific computing. So what is WASM? WASM is an open web standard, living standard, for a virtual binary instruction set that runs on a simple, abstract, stack-based machine. What are its key features? It runs in a secure sandbox. It's extremely portable, being programming language, hardware, software platform, independent, and it's fast. WASM is distributed as these self-contained, completely self-sufficient modules of this virtual instruction set, and they're compiled to native assembly when it's run on the target machine. And what does this all mean for scientific computing? All these properties mean that WASM modules are extremely sustainable. So everything down to the C library and beyond is contained within a WebAssembly module. If you're talking about C and C++, if you're coming from another language, something beyond Python, Go, everything is contained, completely self-sufficient in this WebAssembly module. And where is WebAssembly used? So when you say WASM, many people are familiar with projects that run in a web browser. And this is WebAssembly built with the mscription C and C++ tool chain typically, and a common familiar example to many in the Python ecosystem is Pyodide. This uses mscription to compile C Python and C and C++ based scientific Python packages to WASM. Pyodide runs in a JavaScript runtime like a web browser. However, many people are not aware that WebAssembly also runs outside a web browser and can be run from any programming language or built from any programming language. So you have this terminology. There's a host and a guest system, and they can be written in different languages. They can even just be WebAssembly and WebAssembly. So it's very broad, and there's many different ways that WebAssembly can be used. And this is achieved through developments. There was the initial push to just have WebAssembly for the web browser, but there's been some broader developments, vastly increasing the scope through additional standards called the WebAssembly System Interface. These are standards on how to talk to the systems outside the web browser, and tool chains and technologies and tools to create them. So there's a specific tool chain. For example, a system Python script can use ITK-Wasm Python that will run this C or C++ WebAssembly module, where a native binary C++ package Python would be required otherwise. And this universal deployment capability can dramatically improve the accessibility of scientific codes. So really, write once, run everywhere. It's available everywhere, meaning programming languages, environments like browsers. And so that's kind of WebAssembly in general. And what does this project ITK-Wasm, what problem does it solve? So WebAssembly modules, they are very portable, sustainable. You create one, it should continue to work as is for forever, hopefully, effectively. But they are extremely simple, and they have a limited low-level interface. This interface are module functions that can only use float, so float 32, float 64, and int 32, int 34, integer 32, 34. Those are the arguments that you can have in your functions. And they also give you access to this contiguous linear memory, and that's it. No strings even. That's it. So given that, a programmer will say, okay, how can I take this and effectively program with NumPy with it? So what does ITK-Wasm do? It enables specifically a focus on spatial scientific C and C++ codes. So things like multidimensional images, things like meshes, polydata, point sets, and their usage via WebAssembly. And it does this. What does it do? It provides these idiomatic programming language bindings, packages, and documentation. They're generated from your WebAssembly module. Currently just C++, or you could, it could be other languages in the future. And it provides these canonical scientific programming data interfaces, like you get access to NumPy arrays, you work with them that way, and then also a bridge to traditional scientific file formats. And what are the key concepts that are present in ITK-Wasm? They are processing pipelines, which is this idea of using a WebAssembly module as a processing pipeline, which is as a simple function, pure function, or you could use it like as an actor model, and that's somewhat consistent with this idea in WebAssembly. It's very kind of functional, just the way this stack-based machine works. It supports that type of usage, but pipelines is the idea of a pipeline. And then another idea that's implemented, and this is consistent with how the general WebAssembly ecosystem and tools and standards have evolved, is this idea of interface types. So these are the types that are exchanged on the pipelines as inputs and outputs, and then there's also the ways we deal with this in a way that it can be programming language agnostic. It can be extremely efficient, and ways to do this interchange with these interface types. Interface types being things that can be translated into NumPy arrays, multi-dimensional arrays. That's the idea. What does it look like in practice? What's an example? And so we'll look at an example of how this is applied in a real package. It's a package I created called ngffzar. So ngff stands for Next Generation File Format. Zar is a common web-based, friendly, multi-scale, elegant format. And we'll look at building a multi-scale chunked image in this data model called the open microscopy environment czar standard. So Eric gave a very nice talk generally on what OME is. If you're not familiar with OME, it's from the bioimaging community. But this is a common standard that's being used. And so this is some code that does a real thing of taking some large-scale data in old school form of having a very large monolithic file and taking that to do this chunk multi-scale representation. Mathematically, we know we have to do filtering to avoid aliasing artifacts. So we'll do some Gaussian filtering with this WebAssembly module and have the result be this friendly multi-scale web-friendly image. Example is on the right. This is a brainstem from a person, and a large-scale MRI brainstem. This is a 300 plus gigabyte data set, but it loads dramatically fast, and you can work with interactively thanks to the what we're doing here. So how do you get started and how do you make it happen? There's kind of the effective equivalent to cookie cutters in the web space, the node space. You just create projects. You do create ITK-Wasm, and then you can interactively or on the command line specify what is the interface that you want to have on your module and what are some basic descriptions of the functions and that you're going to be creating. And from that, it'll generate everything you need to build and create all these bindings and deploy packages from it. It will generate for you, right now the focus is on C++, so it'll generate the CMake build configuration for you. And the really nice part of it is that it is standard, simple C++ or build configuration files that you can also use to build the same code with your native tool chains, with what you're used to usually. So you can apply in different contexts. You can also debug and develop it very naturally and efficiently through a lot of tricks here. And you can also do the same thing with your tests. Write the same tests that you can debug and develop with your native tool chains, with your native systems. And this is very convenient because actually what needs to happen here is when the WebAssembly module is generated, it needs to go through WebAssembly interpreter. And because WebAssembly still has all these security, sandboxing guarantees, you don't get access to the native file system unless you explicitly give that access. So this does access, so you can actually access your inputs and outputs to your tests if they're on the file system. And then you specify your processing pipeline just as a simple command line executable, but as the input and outputs, you specify these specific types, and that's because when you're using it as a function in a programming language, you don't do any file system I/O. It does this typing, this interchange efficiently, and it also can self-describe itself from this source of truth to generate all the documentation, bindings, and interfaces from this interface. You provide some documentation there. So from there, you'll generate JavaScript and TypeScript bindings, packages, documentation. And when you do that, it has idiomatic interfaces in all the languages that you work with. So if you're familiar with JavaScript, this is the style of what you would expect a JavaScript function to look like. And it also has really convenient things like generating a live API demo automatically, a website that people can load up and run and try in their browser right away. It also can generate Python packages, so not just Python packages that run in the browser, but ones that run on your system that are pip installable. It contains all the build configuration. And again, we have idiomatic interfaces, Pythonic interfaces, in how you work with these simple, pure functions that are based on your Python dicts and lists and ints and floats and NumPy arrays. And the advantage of that, it works transparently with all the Python tools like Dask, and readily works in this way. And at the same time, it also generates packages you can use with Pyodide in the same way. And practical use cases too, we want to bridge with the rest of the ecosystem. So you can, it also will generate a dispatch Python package that allows you to take in and use non-WASM accelerators. For example, if you had a CUDA implementation built on CuPy, or this QSIM is an image processing library that has some image processing examples for downsampling. You can implement that in a package, and then just in your package entry point say, this implements this function with this priority, and it will run that when that's installed by default. So why is this extremely exciting, and what is happening in the near future? It's similar to some degree to the excitement around something like Czar. So this Josh Mart, who is very active in the Czar community, in OME Czar, he wrote a blog post that contained why I Czar, and part of the excitement there is that you have this open standard that's very simple and efficient that you can use from any of our open source tools across any language to process in a headache-free way. And the exciting and very different revolutionary aspect of WebAssembly is that you can effectively do the same with WebAssembly modules, but you don't have to serialize to disk at all. So you can create an application that's written in multiple languages that works together easily, that is using these WebAssembly modules that are very easy to reason about, simple, that will continue to work without hardly any maintenance, and are performant, portable, and modular, and very interoperable. This is coming through these WebAssembly technologies like WASI and the WebAssembly Component Model, which is a set of standards and tools and ecosystem tools that we comply with in ITK-Wasm, built through this ecosystem of this component model that you can take these building blocks and build them together. So in summary, WASM has the potential to dramatically improve scientific computing because, one, it helps our sustainability, and two, it helps with the accessibility to the scientific code bases that we developed. The other thing to take home is that you may think, well, WebAssembly is just for the browser, but it has applications everywhere. The fundamental two concepts that ITK-Wasm is built around are pipeline modules, one, and interface types. And what it provides are these idiomatic interfaces across multiple languages. In Python, that means NumPy arrays, or the array API standard that facilitates accelerators like CuPy. And finally, this simple, performant, portable, modular, and interoperable WASM modules can be embedded in any language and can be composed into new WASM modules. So I think it's nothing other than the future of computing, and it's very exciting times. So thank you for the opportunity to be with you. I'm happy to answer any questions.
Thank you, Matt. Questions?
Wasn't too familiar with WebAssembly, so I really appreciate the introduction. Do I understand that in order to kind of get into this, you need to learn like C++ in order to get the kind of underlying tooling working for what you're trying to do, or does ITK-Wasm solve a lot of that for you?
Good question. So the earliest tooling was built around C and C++, certainly. But now there is tooling to build WebAssembly from almost any language. So these component model approaches there's a lot more tooling that's growing there. So Python, for Python example, I'm sure many people are familiar with Python, is you can run WebAssembly with Pyodide or build Pyodide compatible packages. So that's one thing that you can do. But you can also, there's tooling out there that many people may not be aware of, where you can take a Python script, and right now it's a Python script and maybe NumPy, and you can take that and build it into a WebAssembly module. And from there, you might need to do some of these tooling, or we can add some tooling to ITK-Wasm so that you can help build more of the interfaces to it. But there's tooling out there to build most languages, JavaScript, so you can do the same with JavaScript. And so where this is going in the big picture is you write code in the language that you want to write in, that you're familiar with, that you're comfortable with, and you can use codes developed in any other language. That's where this is eventually going. So you can maybe use some R tools if you want to quickly, or any other language to put things together.
Thanks, Matt, for the outstanding visuals and talk. One question is, what's the state in terms of multi-threading?
Multi-threading, yes. Yes, so WebAssembly has progressively become more relevant for numerical scientific computing with technologies and standards that have been adopted. SIMD was a big one. So almost all WebAssembly tooling supports SIMD, which is single instruction, multiple data instructions. Your CPUs have the ability to accelerate computation. If you build modern C++, it'll build that through the compiler. Scientific code bases into your modules. That was a big one. Way memory is handled, that's been improved. And then multi-threading has come, it's available in the mscripten tool chain. In practice, when you're working with multi-threading in the browser, it's kind of had an up and down experience of it was available, the technology was available. When it runs in the web browser, it runs in these web workers, which are native web-based threading standards tools that are available. But then it was disabled for some time because of security issues, like some processors. There were some security vulnerabilities. So in practice, like what we're doing, we haven't enabled it yet in ITK-Wasm, but in practice, you want to have something that can run single-threaded or multi-threaded based on how it's deployed, because it might need to be deployed in different ways. And also in ITK-Wasm, so one of the things that was developed was our own thread pool that can work without the native WASM threading that works on these web workers. So you can use that as a background. It's an effective thread pool. And then WASI was developed over many years, and now it's finally into the latest releases of the tool chain, and then also most of the runtimes, they support multi-threading too. So in WebAssembly, it was years ago now that they had WebAssembly Preview 1, and that had the basic instruction sets that they can be compiled and work on ARM, or the virtual instruction set that works everywhere, the basics. Now they're working on Preview 2, and Preview 2 will have all these additional extensions like SIMD and multi-threading. They're all going to be enabled by default in all the runtimes if you're going to support Preview 2, along with this component model, which is formalizing these tooling and interface types and other kind of standards in that way. So it's about here now is kind of the summary.
So the promise of WebAssembly for package developers, and I'm speaking very like long-term and abstract, is you build your native Python package once, and you ship it to the users. They pip install it on whatever system they have now, or possibly exists in the future that you not even know about, and things just work like at near native speed.
Yes.
how close are we to this, you
Yes.
know, utopian?
Yes, that's a good question. So you can install this package, for example, and what happens here. This package, if you look at it, the platform tags for it is, there's no native platform tags. It's Py3 any, just like a pure Python package. And it ships with Python code and the WebAssembly modules as assets. It has a dependency on Wasm time Py, which is a Wasm runtime that is the kind of canonical default runtime. It's maybe like 3 megabytes. And then when it runs, it will, the first time I run it in our ITK-Wasm do some caching. It does that kind of like NumPy, the translation to native code. And this supports Linux, ARM64, AMD 64, Mac, Intel, Mac, ARM, and Windows, Intel. There are, of course, more platforms out there too. Something I'm excited to try at the sprints, if you're interested in trying this or experiencing or trying work with this too, is you can take a WebAssembly module that was built with anything from any language and translate it to C, plain vanilla generic C, and then you can imagine using all the nice packaging tools to build that into a native binary if you needed to have a different platform or you want to explore what that feels like. So it's getting there. It's getting there. We'd love to see if we could make it work on your package if you want to try. Yeah.
Okay, let's thank Matt again. Thank you.